All right, welcome back. So we have another requested video here. I've got a variety of IR and NMR and mass spec data that I'm going to analyze and come up with a plausible structure for. Before we do that, I just want to show the view outside of my office right now. It is a beautiful day here in the Pacific Northwest, but I'm going to focus on this data before I go outside. So let's go ahead and get started. The first thing that I'm going to sort of go through here, starting at the top, is this IR spectrum. I see that we are given a mass spec and a chemical formula, so that's going to be something that is nice to have, easier for us to solve this problem. Again, I've got a UV vis. I don't know what this means, so I'm going to ignore the UV vis. I've never really used UV vis. I just don't know. So we're going to ignore this part. But then I've got a carbon-13 NMR spectrum. It looks like we've got some depth data on here as well. And then I've got my proton NMR spectrum that will obviously be useful. All right, so let's go ahead and get started with our IR spectrum. The first thing that really jumps out at me on this IR spectrum is this sort of broad peak here. This is very clearly an alcohol OH. So an alcohol OH is going to be very broad, and we're going to be able to tell the difference between an alcohol OH and a carboxylic acid OH, because a carboxylic acid OH will be even more broad. So this OH, I think it's supposed to be centered around like 3,200 or 32,000, 3,200 or 3,300 wave numbers for an OH, and then a carboxylic acid is going to be more like this, centered more around 3,000 is going to be the carboxylic acid. So I think for me, this is pretty clearly an OH. And then here, I'm going to say sp3 hybridized CH stretch as well. Over here, this sharp peak here that's coming just above 1600, that could be some sort of aromatic ring. It's not exactly at 1600, so it could be a modified ring or something like that. But at this point in time, I'm not going to label this because I'm not 100% sure. I think that this smaller peak, that might come right at 1600, but because this large peak doesn't, I'm going to leave that alone for now. But I think very clearly an OH and then sp3 hybridized CH bonds. There could be a little hint here of sp2 hybridized CH, but again, when we're first going through this, we want to focus on the things that we know for sure, 100% for sure. Obviously, we know that the chemical formula is C7H9NO because that's given. And from this mass spec, again, we'll talk more about this. I think that this peak at 79 is a very indicative peak. I think that we can draw some conclusions from that, and I'll talk about that in just a second. But if you're curious why I'm saying that, maybe think about our modified ring, a modified aromatic ring that could match up with that 79. So little hint of what's to come. I'm going to go straight down to the proton NMR now. And I think that analyzing the IR spectrum and the NMR spectrum, that's going to be the most useful thing starting out. So when I look at this this NMR spectrum, I've got an expansion of my aromatic region. I see these peaks at 7 and 8. That's very clearly my aromatic region, so I've got some aromatic protons. So going back up here, that could suggest we've got an aromatic ring here. And then I've got this peak here that says exchanges with D2O. It looks like it's a little bit broadened, and the fact that it's around 5 is indicating to me that's our alcohol OH proton. And then I've got two triplets. So both of these are triplets. Triplet. I'm not sure why I spelled triplet as terplet right there, but that means triplet as well. Got a little dyslexic with my I and my R there. But I've got two high triplets. So these look like they're both too high as compared to my OH peak. So this to me is very clearly two CH2 groups right next to each other. And then since I know that there's an alcohol, I might go ahead and put an alcohol at one end, and then some other group's going to be off here, on my other end. But two CH2s, and I know that they're both CH2s because they're both splitting each other into triplets. And then here I would have no more, no other splitting, because otherwise that would split this further, so it wouldn't be a triplet. But here, if you've got two high triplets, I think pretty clearly that indicates CH2, CH2. And I'm going to throw an OH on the end because I know that there's an alcohol here. So these protons here, those are going to be for this signal here at around 4, and then these protons here, they're going to be that signal here at around 3. This oxygen is going to shift this more downfield, right? This signal should be further downfield because it's next to the oxygen, and then this is my OH. So for my aromatic region, the thing that they're sort of hinting at here is that I've got 4 protons in my aromatic region, and I don't have very much symmetry. Like I don't have a mirror plane of symmetry because I've got 4 distinctly different peaks. And this one is definitely even more different than these other groups of 3. So just sort of in the back of my mind, I'm thinking, well, 4 aromatic protons, separate, and then I've got my CH2, CH2, OH. I think that's pretty clear here. So now it's pretty much time to make a guess, to sort of start trying to put all of this together. From this data, I clearly have an OH. I've indicated that on my NMR spectrum. I've got one sort of fragment. I've got one piece figured out, I would say. But that still leaves 5 carbons and a nitrogen that we really haven't talked about yet. And the first thing that I went to was this. So some ring with a nitrogen, right? So I've got my sort of pyridine ring here. I've got my nitrogen. And from this picture here, that's, this fragment is going to weigh 79. So this 79 fragment is a fragment that looks like that. That will equal that mass of 79. So I think that that's a good sort of starting point. Now, trying to sort of put this together with what I figured out down here, I could just throw this on over here. And now I would have my two high triplets. So then since this is bonded to the ring, there's no hydrogen here, so I would get no more coupling. So then this would be a 2 high triplet, this would be a 2 high triplet. So this would be a good first guess. And some of you might be wondering why I decided to put this, alcohol arm in the position that I decided. And the real answer is, 1, I've thought about this for more than just the 7 minutes of this video so far, but 2, it's because of my symmetry. So I knew that we've got this sort of, no plane of symmetry. And then I started thinking about, well, which position should it be at? We can rule out this para position right away because then I would have these 2, so like if this group was here, for instance, then our protons that were here and here, then they would be equivalent, right? So we'd have a mirror plane of symmetry down the middle, and clearly we don't from our NMR spectrum, so we can rule that out. Now the next position that I thought about was here, right? Our ortho position, but again, that would leave a proton right in this position, right, our metaproton, and that metaproton would be a singlet, and it really wouldn't be split by anything else, but we don't see a singlet in our aromatic region. So that's why I decided ultimately to go in this position, and you can see, so underneath here, what I've got is my actual notes from the first time I did this. So I looked over, and I thought it would be interesting to show you all this. This is literally the things that I wrote out the first time that I did this problem. And you can see that I went through, here's my para position, here's my ortho position, and then finally I settled on this one. That's why I've got this nice box around it. And you can see my actual notes, 2 triplets, CH2, CH2, 4 aromatic, no symmetry, right? And then I've got my OH labeled here as well. So this is sort of the raw data that I use to put together, this video. So let's get this looking nice again. So this is my first guess, right? And then we're gonna go through and check it. And I think that this is a nice structure. We've got all of our things sort of accounted for here. Looking at our, our mass spec, the way that I sort of went through this M, plus 123, that's the mass of the whole thing. And then you notice on my other one, I said that this 122, that would be just minus H, so losing this proton. 106, if you subtract minus OH, so if you take off the OH, lose that as a fragment, then you're going to get this 106 left over. We already talked about the 79, that's going to be my pyridine ring. Now this 93, that's going to be a sort of a strange one. So that 93 is actually going to be a protonated nitrogen. So if I protonate that and then cleave here, then I'm going to be left with that peak for 93. So depending on how far you need to explain your mass spec, sometimes these species will be protonated. So keep that in mind. We saw that in a previous video as well. So the last thing I'm going to talk about is the carbon-13, make sure that that all makes sense. So in this, it's a little bit unclear, but I think what this is sort of letting us know is that these pluses equal CH3 or CH, minuses equal CH2. I'm going to put that in parentheses so it's very clear. And then this peak over here, if it's nothing, so nothing, equals carbon with 4 bonds to it, or just no hydrogens basically, carbon with no hydrogens on it. So I think that if we look at our structure, squeeze everything in there, I've got 2 CH2s, so these 2 CH2s will be here. I've got 4 distinctly different peaks in my aromatic region that will be my 4 different aromatic protons. And then this other one here, that would be this carbon, this point here with no hydrogens bonded to it. So I think that all sort of matches and makes sense. Looking at our NMR, again, I've got 4 distinct aromatic protons. I would say that this peak that's sort of set off from the other peaks, that would be this peak here. It should be split into a doublet, a pretty clear doublet from the splitting from this hydrogen here. So we're talking about this proton here. That's going to be split into a doublet, and that proton would be further downfield because it's proximity to the nitrogen. So again, that would be this proton here. So maybe we'll redraw our structure right here. Nitrogen, OH. We'll label these protons as A, these protons as B, then we'll go C, D, E, and F. So A, oh, we forgot, oh yeah, it's right here. It's like we forgot our OH, but it's right there. So our A protons, they're going to be further downfield than our B protons because of the proximity to the OH. So I would call these our A's, these are B's. We didn't label our OH, but that's going to be our OH. This will be C. Now D, E, and F I think is really, it's complicated and it's sort of unclear what's going on here. I might call this F, sort of looks like this might be more of a doublet. E and D, I really don't know. E might be, well, it's hard to tell. It's really hard to tell. So we'll call this E/D, E/D, but I think we can just group all of this, group all of this together as E/F/D, or D/E/F. So all of that sort of would be grouped together there. 3 high signal, right, for all 3 of these species here. Yeah. I guess that's it.